Here. Let's take a look at number 126. Maybe we'll do this one together. A recipe calls for a quarter cup of butter, calculates its mass in grams if its density is 0.86 grams per cubic centimeter. 1 cup is a quarter quart, or 4 cups a quart. That one everybody should have memorized, because those 4 cups in a quart. Normally I wouldn't give that for an advanced problem like this. But our given is a quarter cup of butter. Is it important that it's butter? Yes and no. You know, sometimes we have to be specific, like in that last problem we had to, but in this problem might not be so necessary. But it's not bad to get in the habit. That way you can be sure you'll get the problem correctly. And so I have a hard enough time with students writing any unit. You know, so many students, they refuse to write any units. For example, 80, you know, like for example, if it costs $1,082, it's hard enough to get people to write the dollar sign, you know, or show how things cancel. Somehow they string things together. Maybe they keep track of it mentally, you know, that dollars are canceling out here or whatnot. But if you aren't doing that, then for sure you write the units. In fact, when you start getting to higher and higher levels of chemistry classes, you'll find fewer and fewer students not writing units. And so either the students who stopped writing units started writing units, as they're going to have to, or the students who stopped or who never wrote the units never continued on, you know. And so think about that. So you got to get in the habit of writing the units no matter what. And sometimes you have to go above. Like, so this one, not just a quarter cup, but a quarter cup of butter, because it might make a difference if it's butter or water or whatever. So we start off with a quarter cup, and then we do this. This is why I picked the advanced problems. I picked the advanced problem because we have to do more of this. I picked the advanced problem in Chem 1A is because we either going to cancel out what? We're going to cancel out cups, or we're going to cancel out cups of butter. Now, if we think, do we have anything that would cancel out cups of butter? No. There was nothing given in the problem. So the only thing we can cancel is cups, not cups of butter. And so that strategy, you know, doing this little thing, this little extra step means you can solve the advanced problem versus not being able to solve the advanced. Well, maybe you can still solve the advanced problem, but it makes it a heck of a lot easier if you just add this little extra. I mean, it's a little bit more bookkeeping work, a little bit more, you know, tracking, but it'll pay off in the end. But we do have something that relates to cups. In fact, like I said, 4 cups you should know is 1 quart. What they want to know is they want to know the mass in grams. So I don't know where else to go here, so we'll just say we're going to have this many quarts of butter. And then from quarts, well, the only thing we can do with quarts, or quarts of butter, actually I don't know anything with quarts of butter, so we'll just go with quarts. Only thing I know about, there are 4 quarts in a gallon. These are all definitions. So, and if I go the wrong path, it doesn't matter. I don't really care. You know, I'll just back up if this turns out to be wrong, and then try again. And so now I'm at gallons of butter. Where can I go from gallons of butter? Well, I know 1 gallon is equivalent to how many liters? 3.785 liters. And so now I have liters of butter. See, I don't have a particular strategy. You know, we're just following along this path, and if it continues, great. If it dead ends, it's okay. And so from liters of butter, do I have anything that gets rid of liters of butter? No. But I do have the density of butter of 0.86 grams per cubic centimeter. And I know what a cubic centimeter is. A cubic centimeter is the same thing as a milliliters. Yeah. So I'll just go to milliliters here. 1,000 milliliters, right? Per liter. So far, as far as sig figs go, I have 2 sig figs here. How many do I have here? Infinite. How many do I have here? Infinite. How many do I have here? 4. So I could probably get away with 3, but I'll just go with 4. I have infinite here. And so now I have milliliters of butter. So I don't have anything with milliliters butter, but I do have something with cubic centimeters butter. And so I'm going to go from milliliters to cubic centimeters. Do I need to cube this whole thing? No. Okay, so milliliters cancel. That leaves me with cubic centimeters of butter. Now, do I have something that cancels out cubic centimeters of butter? I do. That's the density here. This density is for butter. And so this just says there's 0.86 grams of butter per cubic centimeter of butter. And so here, my cubic centimeters of butter cancel out cubic centimeters, and I go from volume to mass. So calculate its mass in grams. Well, this is grams of butter now. I didn't really have to carry the butter because the butter wasn't changed to anything else. You know? Sometimes we have this much butter and we need a certain amount of flour. So for every cup of butter, we need, let's say, 4 cups of flour. In that case, you know, we're switching from butter to flour. This one stays butter all the way through. Yeah. And so in this case, I really didn't need to put butter down because everything all butter. But in a typical problem, it doesn't stay the same all the way through. In a typical problem, we change it to other things. How many? Okay, so if I have 1 cup of butter, how many cups of sugar do I need, you know, for a particular recipe? That's what we do here. And so in the end, I'm allowed 2 sig figs. So I want to carry more sig figs than I'm allowed. And so I'll just punch this out in the calculator and see what it comes out to. Divided by 4. Does somebody have the answer? What did you get? 50.8609. Okay, since we're only allowed 2 sig figs, we'll just carry maybe a couple of extra here. So 50.86 should be fine. And then we'll round this to 2 sig figs, which will give us 51 grams. All right, normally we double check it, you know, does this sound reasonable, that kind of stuff. But in this case, we have our answer book, so we can save a little bit of time and see what the answer book got. And the answer book got 51 grams of butter. And so we're good. They have this set up here, which is number 126. Well, actually, they set it up, and they did it the exact same way we did it here, using 3.785 liters per gallon. All right, that's 126. Take a look at 124. Shadows coming in here, so move this up here.
Does it use my book? Mine's like flat. Yours is like this.
It's okay, I think. Unless, can you guys read this okay? Or is it annoying? A welcome rainfall caused the temperature to drop by 33 degrees C Fahrenheit after a sweltering day in Chicago. What is this temperature drop in degrees Celsius? So when we're dealing with temperature, one of the things we have to keep in mind is that a delta T or is that a T? Delta T's we use dimensional analysis, T's we have to use algebraic equation. This is a T. Okay, if this is a T, what is the temperature drop in Celsius? So we want the temperature in Celsius. So the temperature in Celsius is equal to 5/9 the temperature in degrees Fahrenheit minus 32. Is that the correct? You know, I just rearranged the other equation that we had. Is correct? And so let's go ahead and plug that in. 5/9, and the temperature in Fahrenheit is 33. This is minus 32. So this comes out to 1 over 1.8. is it? 15? 15.2. Is that what other people got? Let me try it. So 5 divided by 9. Essentially, this comes out to 1 degree, so it's 5 divided by 9. 5 divided by 9. I got 0.55.
Yeah, it should be.
0.55.
Can you use 1.8 instead of 5.9?
You could use 1.8, except it'd be 1 over 1.8, because 9/5 is 1.8.
So it's 1 over 1.8 times what?
Yes. 9/5 is 1.8. 5/9 is 0.555. Now, does that make sense to you? Here, if the temperature dropped 33 degrees Fahrenheit, it's a pretty big temperature drop. And so the temperature might have been 99 degrees one day, and then the next day it's 60 degrees. It would be sort of 66 degrees. It would be a 33 degree temperature drop. And so in terms of Celsius, it's like a half a degree Celsius. So for every about 0.6 degrees Celsius, we have about 30 degrees Fahrenheit. Does that make sense to you? Yeah? So like a 1 degree Celsius, let's say the temperature dropped by 1 degree Celsius. Temperature drop by 1 degree Celsius, what would that temperature drop be in terms of Fahrenheit? Well, it should be, this is about double. And so it should be about double, so I'm guessing around 60 degrees. If the temperature drops by 1 degree Celsius, then we have a 60 degree Fahrenheit drop. Does that sound about right? No. Actually, this is not a temperature problem. This is a delta T problem, or change in temperature. And so, if this were a temperature problem, then 33 degrees Fahrenheit is 1 degree above freezing, right? 32 degrees, so we're at 33 degrees, 1 degree above freezing. What is the Celsius? Well, the Celsius is going to be just above freezing. And since the Fahrenheit is about twice the Celsius, well, 1 degree above freezing for Celsius would be about 2 degrees above freezing for Fahrenheit. Therefore, 1 degree above freezing for Fahrenheit is about a half a degree above freezing for Celsius. So this equation's right. If the ambient temperature is 33 degrees C, it's freezing cold. It's only 1 degree above freezing. And therefore, the Celsius is going to be like a half a degree above freezing. Does that make sense? But is this saying that we're just 1 degree above freezing? No, this is saying there was a 33 degree temperature drop. And so in that case, we don't use algebra for that one. We use dimensional analysis. And so for dimensional analysis, it would go like this. If we had a delta T, this is delta T. If we had a delta T of 33 degrees Fahrenheit, then I know that there are going to be 180 degrees Fahrenheit for every 100 degrees Celsius change. I didn't round it to the proper number of sig figs. We'd use the Fahrenheit. It's to 2 sig figs. I always write 1 extra or more, and so I need to round that to 0.56. But that's the wrong answer. Yeah. we can't do this. You know, we could do this algebraically. Do you know how to do this algebraically? If you can't figure this out here, or if you couldn't figure this out, there's a way to do this algebraically, but it's long. Let me set it up for you, and then let's see how much time we have. Enough time. I'll set it up for you. But before I do that, let's calculate this. So if we had a 33-degree Fahrenheit drop, so it's 33 times 100 divided by 180. That would be an 18.3 degrees Celsius drop. In other words, it would be an 18 degree C drop. And so if we had a 33 degree Fahrenheit drop, we had an 18 degree C drop, Celsius drop. Now, we could have done this algebraically, which I didn't set up, but you know, this is often done to solve these problems too. When you're trying to solve a problem like this, you just pick a number. You pick a number like, okay, if it's 33 degree Fahrenheit after sweltering days, so let's say it was 99 degrees in Chicago. So we're at 99 degrees Fahrenheit and the temperature dropped minus 33 degrees Fahrenheit, and so we're going to be at 66 degrees Fahrenheit. And so one day we went from 99 to 66. So what we do is we calculate degrees C here. A 99 degree Fahrenheit is how many degrees Celsius? And so degrees Celsius is equal to 5/9 times degrees Fahrenheit minus 32 degrees, just rearranging the equation. And so the degrees Celsius, we can plug in 99 here. And so what I do on the calculator is I'd go 99 minus 32, and then hit equals, and then times 5 divided by 9, 37.2. And so if I'm at 99 degrees Fahrenheit, this is going to be 37.2 degrees Celsius. I'm not going to round it yet because I'm only allowed one rounding. I want to round at the very end of the calculation. So I'm going to carry an extra digit, although I'm only allowed one. Now 66 degrees Fahrenheit is what in Celsius? So that's going to be 66 minus 32 equals, and then times 5 divided by 9, 18.8. And so this is going to be 18.8 degrees Celsius. And so what was the Celsius drop? Well, we went from 37.2 down to 18.8. So what I'm going to do is I'm going to go 37.2 minus 18.8 equals 18.4. And so the drop is minus 18.4 degrees C. Now I'm only allowed 2 sig figs, so this is going to round to minus 18 degrees Celsius. And so that's a change here. Well, 33, well, this is minus because we lost it. It's going to be minus 18 degrees C. You see that this is the way we could have done it algebraically to get the change in temperature by calculating the temperatures first and then figuring out the delta T, or we could have figured out the delta T directly using dimensional analysis. So it's something you have to pay attention to.
You didn't even have to use sunshine. You could just pick any.
Yeah, you could pick any number. I just picked 99. This is what you do. If you don't have enough information to solve it, you could pick any number. And you can say, assuming we're starting at that number. And so I might have picked something easier. I could have picked, you know, if you're going to do this, you might as well pick easy numbers, but it says sweltering day in Chicago, so I was thinking 99 or 100, you know. Just pick a number. Did they give you the number? No, they didn't, so you can pick any number you want. It should work. Okay. All right, this is a challenge problem because we're so used to using the formula, degrees Fahrenheit is equal to 9/5 degrees C plus 32. This doesn't work in this case. This is temperature change. How many grams of milk are in 12.0 fluid ounce glass? The density of milk is about 64.4 pounds per cubic foot. There are 7.48 gallons per cubic foot, and by definition there are 4 quarts per gallon and 32 fluid ounces per quart. you know, even though I do these, maybe I shouldn't be doing the blue problems. Maybe I should leave those to you. But even though I do these in class, you should repeat the calculations at home. You know, make sure. You should repeat the calculations without looking and see if you can get it. But let's go ahead and do this one. And then it's like memory, you know. If I gave you a list of numbers or a list of names to memorize, right? You might hear it once in class, right? But then you'd go home and see, do I remember that? It's the same thing here. Do you remember how to do the problem? That kind of thing. And the more exposure you get to these problems, the better you'll remember what to do. And then you're more apt to be able to do problems that you haven't encountered before as well. Okay, the shadow keeps moving. So we'll go ahead and do this. Now we're going to start off with 12.0. 12.0, and I'm going to abbreviate fluid ounces, FLOZ, for fluid ounce. And then we have a choice. But now I know that often it's important that I include what it is. It's milk, and not just fluid ounces. It's fluid ounces of milk. And so the thing I need to do is I need to get rid of fluid ounces, or I need to get rid of fluid ounces of milk. Do I have anything that will get rid of fluid ounces of milk? That would be better. Is there? No, there isn't. So I'm only going to get rid of fluid ounces. And how can I get rid of fluid ounces? There are, by definition, 32 fluid ounces in every quart. And so I'm going to go from fluid ounces of milk to quarts. Or I could, you know, there's another thing. I could go from, you know, what a cup, how many fluid ounces are in a cup? 8 fluid ounces in a cup. How many fluid ounces in a pint? 16 ounces in a pint, you know, etc. So I don't have to go straight from, I could go from, let's say, fluid ounces to cups, and then we know how many cups are in a quart, or how many cups are in a gallon, etc. And so this conversion factor, there are many choices we could have done here. But anyway, this is given, so we'll just go ahead and use it. Now we have quarts of milk. Do we have something that gets rid of quarts of milk? No. We don't, but we do have quarts of gallons. So 4 quarts in a gallon. Now we have gallons of milk. Is there something that gets rid of gallons of milk? No. But we do have something that gets rid of gallons. What is it? This is pretty convenient. They give us gallons to cubic feet. 7.48. Do you think that's exact? 7.48 gallons in a cubic foot. Do you think that's exact? No. That's just 3/16. All right, now we have cubic feet of milk. Is there something that gets rid of cubic feet of milk? Or just cubic feet? Yeah, we have the density. Now the density is only for milk. That density wouldn't be valid for water or whatever else. This is the density for milk. And this is not exact either, but for every cubic foot of milk, we should have 64.4 pounds of milk. So this is specifically just for milk. And so now I can get rid of cubic feet of milk, and now I got pounds of milk. They want grams of milk. And so where should I go next? Yeah, I would go pounds to kilograms. How many pounds are in a kilogram? 2.20. Is that enough sig figs? No. You want to go 4 sig figs maybe. 2.204 pounds in a kilogram. Is that right? Yeah. And then we want to go to grams. So there are 1,000 grams per kilogram. Okay, and this takes us to grams of milk here.
So do you want us to memorize these conversion factors, or going to give it to it, or how you want us to do it?
Some of them you have to have memorized.
Like 2.2 204.
No, you don't have to memorize that. The exact ones you should have all memorized. The measured ones or approximate ones, you don't memorize.
So
All right.
The answer is
Yeah, the answer is 366 grams to 3 sig figs. 366 grams. But you should show me it before rounding. Remember that acre foot problem? Acre feet? Lake Oroville? Alright, this is similar to that in one way. A woman has just given birth to a bouncing 6 pound 7 ounce baby boy. How should she describe the weight of her child to her sister who lives in Sweden in metric units, of course? 6 pounds 7 ounces. There's a composite unit there, you know, there's 2 parts to that unit. So we might try it like the problem we did, you know, 6 pounds and 7 ounces. We might try to convert ounces into pounds. Do that. How many ounces in a pound? 16 ounces in a pound. But, you know, this is not 6 pounds times 7 ounces like the problem of the acre feet. This is 6 pounds plus 7 ounces. So if we convert 7 ounces into pounds, what does that come out to? So this is going to be a kind of a weird one. 6 pounds plus, okay, 7 divided by 16 is how many pounds? 0.437. How many sig figs are we allowed? 1. And so this is addition. Addition is going to be a little tricky. This one we call exact. You know, the baby is definitely more than 6 pounds. And so there's no uncertainty there. The mass or weight is greater than 6 pounds. There's uncertainty here. And so this is 1 sig fig. And so we have 1 sig fig here, but I'm not going to do that yet. And so what I'm going to get is I'm going to get 6.4, and so I'm allowed that 1 sig fig. When we do addition or subtraction, we keep track of the uncertain digit. So this would be the uncertain digit here, and that means these are extra digits here. And so altogether we have 6.437 pounds. And then we can convert it to kilograms using 2.20 pounds per kilogram, or 2.204 pounds per kilogram here. Kilograms. So I get 2.92 kilograms. Now, the uncertain digit is here, just keeping track. And so this is going to come out to 2.9 kilograms. Now, doing addition and subtraction, the sig fig rules are different. So let's go back and just take a quick look at the sig fig rules for addition and subtraction. Here. Let's take a look at number 11. What we have to do with these is we have to either write it in decimal form, or we have to make sure that the exponent is the same. So this is 6.38 times 10 to the 7 plus 4.01 times 10 to the 8. And so 6.38 times 10 to the 7 plus 4.01 times 10 to the 8. Now, when we're thinking about the measurement, there's a guess digit or estimated digit. And if this is a measurement, then this 8 is the uncertain digit. You know, they're kind of estimating where that falls between the lines. It's like 8/10 of the way between the lines. And this 1 is the estimated digit here. So that's where our uncertainty is. Okay, for multiplication and division, we say there's 3 sig figs, 3 sig figs. Our final answer should have 3 sig figs. But this is addition. And so for addition, you have two options. One, get it in decimal form. Getting this in decimal form, I need 0 point, then I need 6 zeros. 1, 2, 3, 4, 5, 6 zeros, and then a 6, 3, 8. Okay, this would be the decimal form of that. Okay, then we can keep track of the uncertain digit, which is this 8 in the end. Okay, and then plus, okay, I'm going to get this into decimal form, so 0.0, I mean 0 point, okay, now I need 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros, and then a 4, 0, 1. And this 1 here is uncertain. And so when I add these up, I'm going to get point, okay, then I got to go 1, 2, 3, 4, 5, 6, then I get a 6, 3 and 4, 7.
Are those supposed to be to the negative power? Or like,
Oops. Positive. Sorry. This example I'll do negative. It's an easy fix. Let's do it to the negative power.